Good day everyone, welcome back to our channel. Today, we will have a part 2 in our video tutorial covering different integral topics. In this video, we will be focusing on the formulas and how and when we can use those formulas. So, let us start with the first topic, area under a curve. The area under a curve represents the accumulation of quantities often found between a function y is equal to f of x and the x-axis over an interval a to b. With the formula, area is equal to the integral of f of x dx from a to b, which f of x is equal to y. So, let's try to illustrate. We have the y and the x-axis, and let's imagine that we have a curve. So in this curve, we have a to b, and we are going to get the area of this curve. So let's get a strip here. So let's write this into bigger one. So here we have this, which is the dx, and here is the y. Solving area under a curve is crucial in estimating material use in construction or manufacturing. It is also used in calculating the land area. So now let's try an example. We have a curve 9, y is equal to x squared, and 9x is equal to y squared. So here we have to isolate either y or x. So here we have x is equal to the square root of 9y, and here we have x is equal to y squared all over 9. So let's make this an x of 1 and x of 2. So x of 1 is equal to x of 2. X of 1 is equal to the square root of 9y, and x of 2 is equal to y squared all over 9. So let's get the value of phi. So we have there the square root, so let's square this one. So let's cancel the square root here, so that will become 9. Y is equal to y raised to 4 all over 9 squared is equal to 81. So here we have the 81, so let's multiply this by 81 to cancel this, and here we have 81, so that is equal to, so 81 times 9 is equal to 729. Y is equal to y raised to 4. Since we have the y here, so let's divide this by y to cancel y. So that is equal to y cube is equal to 7 to 9. We have the cube here, so let's get the cube root, and y is equal to 9. Since we have the value of y, so let's plug it here. So x of 1 is equal to the square root of 9 times 9, and we all know that this is 81, and the square root of 81 is equal to 9. So that is the value of x of 1. So now let's try the x of 2. So 9 squared all over 9 is equal to 9. So that is now the value of x of 2. So now let's try to plot the curve. So let's put the given curves here, and we have the value of x and y, which is the 9. And so let's plot this one. So since this is a square root, so that is a parabola facing upward here. So, and this is just the same but in y squared, so that is here, and we have 9, 9, so the intersection is 9 and 9. So now we can now get the area of this one. So here we have to get a strip here, so that is look like this with a dimension dx and y. So now we can use this to solve for our problem. So the area is equal to the integral of a to b, since we have the value of our x and y here, so that is 0 to 9, and we have the value of our f of x, which is the y, which is the difference between the y high and the y low. So now let's get the value of y in terms of x. So that is y high is equal to the square root of 9x, and the y low is equal to the x squared all over 9. So let's use this. So since y is equal to the difference between the y high and the y low, so let's put it here times dx. So we have now the y, which is here, and the dx. So we can now use this formula to get the area of the two parabolas. So that is equal to the integral of the square root of 9x minus x squared all over 9 times dx from 0 to 9. So now we have the integral of 3 multiplied by x raised to 1/2 minus the x squared all over 9, so multiplied by dx. So we can now integrate this one, so that is 3 times x raised to 3 over 2 all over 3 over 2 minus x cubed all over 9 times 3. So from limit 0 to 9. So now we have this one, so let's multiply it from the numerator. So that is equal to 2 times 3 all over 3. Since we have this, so cancel this one. So this now equal to 2x raised to 3 over 2 minus x cubed all over 27 with the limit from 0 to 9. Since we have the 9 here, so let's plug the value to x. So we can now use our calculator to solve this one. So that is equal to 27 square units. So this is now the value or the area bounded by the two parabolas. Now let's proceed to our second topic, which is the centroid, or the center of mass for area. The centroid is the balance point or average position of a shape or object. It is crucial in engineering design for weight distribution and determining where to place supports in construction. It is also used in balancing beams or objects. And we have a formula, AT, which is the area total multiplied by y bar is equal to the integral from a to b, and d multiplied by dA. So let's try first to get the value of this one. So let's use the graph. The dA is the distance between the centroid to the axis. It's either x or to the y axis. So for the y bar, it is area total multiplied by x bar is equal to the integral from a to b multiplied by d and dA. Now that we have the formula, so let's try to solve an example. So let's just use the previous example, which has a limit from 0 to 9, and it is 0 to 9 here. So that is from 9 to 9, and the area, which is 27. So let's get the y bar here. So it is the a total, or 27, multiplied by y bar is equal to the integral from 0 to 9 here. We have the limit, so let's get the step here. This is dx and this is y. So from 0 to 9, and we have the y, or the distance, and let's put here the formula. So the d here, which is located here, can be solved using this one. So here, from here, so let's imagine that we have here an object which is 2 2 meters from the ground, and let's say this is 5 here. So the total is 7. So to solve the y height, which is equal to 7, so let's just add this and multiply by 2. So this is 7 plus 2, which is here, and this one. So let's divide this by 2 to get the average. So 7 plus 2, which is equal to 9, and 2 here, so that is equal to 4.5. So we have 4.5 here. So to check if this is correct, so let's divide the 5 here to 2, which is 5 over 2, which is equal to 2.5. So 2.5 plus 2, which is the 4.5. So that is equal from our solution or our answer here. So let's use this formula. So let's now use or solve this one. So the y here, the y height, which is the square root of 9x plus x squared all over 9 divided by 2. So multiplied by the square root of 9x minus x squared all over 9 multiplied by dx. We have here the 2, so let's put it here, and the 27. So that is now y bar is equal to 1/2 multiplied by this one, so 1 over 27. So multiply this one, that will become 1 all over 54 multiplied by the integral of from 0 to 9. Here we have the difference over square, which is a minus b squared, so that can be written as 1 minus b multiplied by 1 plus b. So just like this, we have now this one, so that is equal to the square root of 9x minus x squared all over 9 squared. So let's erase this one, and that is multiplied by dx. So we can now simplify this one, so that is equal to 1 over 54, the integral from 0 to 9. Here we have to cancel this, so let's put the integral multiplied by 9x minus here x raised to 4 all over 9 squared is equal to 81 and dx. So from here we can now get the integration of this to solve for the y bar. So let's erase this first. So let's integrate. So y bar is equal to 1 all over 54 multiplied by 9 x squared all over 2 minus x raised to 5 all over 81 times 5 is equal to 405. So 405 here, and we have the limit from 0 to 9. So we can now solve this using our calculator. So y bar now is equal to 4.05 units. So based from our graph here, we have the limit from 0 to 9 for both x and y. So our graph is symmetrical, so now we can conclude that our x is equal to y. So since we have the value of y bar, which is 4.05, so our value of x is also this one. Now we are done with our second topic, which is the centroid. Now let's proceed to our third topic, which is the area moment of inertia, or the second moment of area. The area moment of inertia measures how a shape resists bending or rotation. That depends on the distribution of area about an axis. So it is crucial in structural analysis in buildings and bridges. It is also used in beam descents and to prevent buckling in columns. The formula for the inertia about x-axis is equal to the integral of y squared multiplied by dA. For the inertia about y-axis, it is equal to the integral of x squared multiplied by dA. From our graph earlier, that looks like this one. we have the y which is from here. So from solving about x-axis, so it is always parallel to the axis, and our x is here. So when solving about x-axis, it is always like this one. So when we try to solve about an y-axis, so it is always parallel, so it looks like this one. So now that we have the formula and the graph, let's try to solve an example. So let's put the graphs here for you to have a guide in solving our problem. Now that we have the graphs here, so let's also put which axis are we going to solve. So here it is a moment about x and here is the moment about y. So let's now proceed to solving. Let's solve for the moment of inertia about x-axis. So that is equal to the integral of, we have the limit 0 to 9, that is y squared multiplied by the dA, since we have the dA is equal to dy times x, and our x height which is equal to the square root of 9y, and we have the y squared all over 9 multiplied by dy. So we can solve this directly using our calculator. So just a reminder, this tutorial is focused mainly on the formula and the process of solving. Let us now plug in our values in our calculator. So that is now equal to 562.37 units. So again, since our x and our y is the same, so we can conclude that our area moment of inertia about y-axis is also this one. And that's all for our third topic, which is the area moment of inertia. Now let's proceed to our fourth topic, which is volume of solids. Volume is the 3D space occupied by an object. So by using calculus, we can find volumes of solids generated by rotating a region about an axis. In solving volume of solids, we will be using these methods and formulas. So when do we use each methods? So for this method, it is used when rotating a region about the x-axis or the y-axis, and the region is bounded by a single curve. For the second method, which is the washer method, it is used when rotating a region about the x-axis or y-axis, and the region is bounded by two curves, and it has a hole or gap. For the third method, which is the shell method, it is used when rotating a region about the y-axis or x-axis, and it's easier to integrate with respect to the other axis. So those are the conditions that we have to look in order for us to use each method. So for us to solve an example, let's try v is equal to pi, the integral from a to b, and y squared. So we have y here, so let's use the r instead of y since it is a circle. So r squared dx. So let's put it here. So now we have this formula. As you can see, this is this method. However, we have here the graph which is look like this. So we have the upper y and the lower y. So with that, when we rotate this about x-axis, it will look like this. So let's draw here. So it will now become a ring-like object. So here we have the upper y or the radius high, and we also have the low radius. So the value of r now is equal to the RH or the r height minus the r low. So let's put it here. The integral of, since we have the limit from 0 to 9, so let's put the integral from 0 to 9, and we have the pi. Let's put the pi here in the outside, and our value of r, which is RH at r low, is equal to the YH and the y low. So that is now equal to the square root of 9x minus x squared all over 9. And we get this value from here, and this value is from here. So this is squared and multiplied by dx. So let's simplify this first. Let's write this the above because we don't have a space now. So that is equal to pi, the integral from 0 to 9, and this will be cancelled, the square, so this will become 9x minus x raised to 4 all over 81 multiplied by dx. So let's integrate this first. So this will become equal to pi. So let's write, so this is equal to pi. We have the 9x squared all over 2, and we have x raised to 5 all over 81 times 5, which is equal to 405 from limit 0 to 9. So let's use our calculator to solve this one. So that is now equal to 4,374 all over 5 pi, or we can get rid of the pi, so let's erase this first. So that is now equal to 2,748.27 cubic unit. So this is now the volume bounded by the two parabolas. And that's the end of our topic, volume of solids. So for the next topic, we have the work involving pumping a liquid. Work is the energy required to move an object or fluid over a distance against a force, like gravity. So the formula for work is equal to the force times distance. So let's imagine that we have a cylinder here that is full of water, and we have a pump here. So we have now the differential work. So let's put dw here. So to get rid of d, so let's integrate this. So that is equal now to w is equal to the integral of f and d. So we have the limit from a to b. So we have here, this is the a and this is the b, since this is the water. If we have the water level here, so our value of b is from this one. So let's erase this first. So let's make an example. So we have the cylinder, and we have here the water and the pump here, and the radius or the diameter is 2 and the height of the bottle is 4, and we have the 2 here. So let's solve for the work on how much work we have needed in order for us to fully pump out all the water. So we have here work is equal to the integral from a to b, which is here, and to b, and we have 0 to 4. So let's write the formula F and D. And we all know that the force is equal to the pressure multiplied by the area. And the pressure is equal to the density times the gravity times height. We all know that the density of the water is equal to 1000 kg per cubic meter. So 1000 multiplied by 9.81, and the height here is, let's get a strip here. So since this is a 3D, so it will become look like this. So let's draw it here. So this is our dy, and we have our radius here. So our radius is equal to 1 since we have the 2. So our height is equal to dy. So let's now substitute our values. So that is now the integral from 0 to 4, and f is equal to 9/8 multiplied by dy. And for the area, we have the circle, which is the pi, and the radius is 1 squared. So now for the d, we have here to here. So let's denote the dy to the ground, so as y. So here we can get since this is equal to 4 plus 2, which is 6, so our height now is equal to 6 minus y. So that is now equal to, let's pi multiplied by 9,810, the integral from 0 to 4, and we have the y values, which is the 6 minus y multiplied by dy. So let's integrate this. So we have pi multiplied by 9, 8, 10, and we have here, so this is now equal to 6y minus y squared all over 2, and we have the limit from 0 to 4. So we can now use our calculator to solve this one. So that is equal to 156,960 pi, and the unit joules. So this is how much work we needed in order for us to fully pump out all the water in this cylinder. So if we use another fluid instead of water, remember that it has a different gravity or a specific gravity. So therefore it has a different density compared to water. So that's all for the topic, work involving pumping a liquid. Now let's proceed to our last topic, which is the length of the curve. The length of the curve refers to the measurement of the distance along a curved path, and it is calculated using the integration. And it also determines the actual length of a curve between 2 points, taking into account its shape and bends. And it is crucial in designing the roads and bridges and many more applications. And it has a formula. The arc length is equal to the integral from a to b, the square root of 1 plus dy all over dx squared dx. So let's try an example. Find the length of a curve y is equal to x squared from x is equal to 0 to x is equal to 1. So let's use this formula in order for us to solve this one. So let's rewrite the problem. We have y is equal to x squared from x is equal to 0 to x is equal to 1. So to solve this, let's get the derivative of this. So dy is equal to 2x dx, and let's divide this by dx in order for us to get the value of dy all over dx, which is this 2x. So using the formula, L is equal to the integral from 0, we have the limit 0 to 1, and the square root of 1 plus we have the value of dy over dx, which is 2x raised to 2, and the dx. So let's simplify this one. So this is equal to integral from 0 1. So 1 plus this is 4x squared dx. So let's use the calculator to solve this one. So that is now equal to 1.48 units. So this is now the length of a curve y is equal to x squared from x is equal to 0 to x is equal to 1. And that's the end of our part 2 on mastering integral calculus. I hope you learned something, and thank you for watching.